Temperature outside here today is a balmy -16 with light winds and cloud cover. So to escape, we're going to go to Palau, at least briefly. Palau has an average summer temperature of 28 degrees centigrade, and in the wintertime, temperatures drop to a frosty 27.8 degrees centigrade. That all seems great, except that all of Palau is very, very close to sea level at this time. What this means is with current models of global warming and sea level rise, these islands will be covered with the Pacific Ocean in your lifetime. So we're going to talk about carbonate rocks today. And one of the reasons we're going to talk about carbonate rocks today is that they're very, very important for recording ancient environments. That includes aspects of the ancient environment, such as the amount of CO2 in the atmosphere and temperature. We can get those kind of signals from isotope values of carbonate rocks if the carbonate rocks record those accurately when they're being produced. So that's what today's story is going to start on. And this is from a talk I gave about 10 years ago at the Earth System Processes 2 meeting. And what I was discussing was some of the work I did as a master's student in the Bahamas and the Florida Keys. The Bahama Banks are located here. This is Grand Bahama Bank or Great Bahama Bank, and Little Bahama Bank here. This is tongue of the ocean, very deep water in the Florida Straits. I also worked over here in Florida Bay and along the Florida Keys Reef track. The reason I was doing this chemical work underwater, for the most part, is that places like this, environments like this, and down here in Guantanamo Bay, which is not the same as Guantanamo Bay, which is over here. Guantanamo Bay and the Bahamas and Florida represent periods of time in the geologic past when the continents were covered with carbonate platforms. Carbonate-producing organisms covered North America at various times in the geologic past. Therefore, if we can get an understanding of what's going on in the modern places like this and this, we can better interpret what happened in the past. Now, for example, this is Ordovician paleogeography. This is what North America looked like, at least our best estimate, about 450, 460 million years ago. As you can see, much of the US and quite a bit of Canada, including here in Saskatoon, was covered with seawater at the time. This would have been relatively shallow seawater. It's called an epiric sea, epi-eric. Epi means on top of, so a sea that's on top of a continent is what that means. So if we take the carbonate rocks that were produced during the Ordovician and we analyze them for their isotope values, we can get a handle on, again, how much CO2 was in the atmosphere at the time and the temperature of the water at the time, if the rock represents the original signal. That's the key. Does it represent the original signal? Carbonate platforms are going to generate significant amounts of carbonate. About 30% of the world's carbonate that's being produced at any given time is generated on these platforms, which represent a very small amount of the Earth's surface area. So a lot of carbonate produced in relatively limited areas. Most of this carbonate is going to be produced by algae, and a significant amount will be produced by coral. But algae are doing the real work here. Most of this material you see here is carbonate that was generated by algae. So we mentioned last time that lakes and marine environments are chemical mixing vats. This is definitely a chemical mixing vat, and it's mixing chemicals. In this case, it's mixing carbonate chemicals. We have three types of carbonates we're going to talk about today. Calcite, which is CaCO3, high magnesium calcite, which is calcium carbonate with about 15% or so magnesium. That formula is calcium carbonate as well, but with a significant amount of magnesium in those crystals, in that lattice. The result is this is much less stable than this. If anything's going to dissolve in an environment where there's calcite and high mag calcite present, it's going to be the high magnesium calcite. Aragonite is another form of calcium carbonate that's present here. In fact, it's the dominant form. It has the same formula as calcite, CaCO3. It does not allow magnesium to play its reindeer games, though. So aragonite is magnesium-free. It is also slightly less stable than calcite. So high magnesium calcite and aragonite will tend to dissolve in this chemical mixing vat that we call Belize in this case. Once deposited as sediment, these carbonate grains are going to start to undergo diagenesis. We call this syndepositional diagenesis because the diagenesis, the rebirth, the change chemically, is taking place as material is being deposited. Syndepositional means as deposited. So the chemistry is changing as this material is accumulating, as plants and animals die and leave their calcium carbonate skeletons behind. Those skeletons undergo pretty rapid chemical change. Just adding some more complication to accelerate this chemical mixing, we have organisms such as ghost shrimp. Callian acid or ghost shrimp are about the size of the kind of shrimp you would buy for, say, a shrimp cocktail at a store or a restaurant. But these shrimp dig meter-deep burrows, so they mix the sediment up to a depth of 1 meter. And when they do that, they're bringing fresh organic matter from the surface down into deeper layers of the sediment pile. And it's in those deeper layers in the sediment pile where there's no oxygen that sulfate-reducing bacteria take over the chemical reactions. So these sulfate-reducing bacteria generate acids that dissolve the least stable phases of carbonate preferentially. They're going to dissolve the high magnesium calcite and aragonite. That's going to produce an excess of ions in the sediment that is then going to result in a reprecipitation of calcite in the sediment. So what we've done is essentially taken a record, an environmental record, that is accumulated by the organisms that live in this environment, and we've changed it. We've rewritten it. We've written over the file. The information that's recorded by this material is actually within the sediment pile, not the external environment. Unfortunately, my best underwater photos were all taken with slide film and an old Nikon S5 camera. So I don't have access to those for this lecture, so I'm using some pocket camera photos that I took, about 10 years ago or so. This image here represents the fore reef environment. So this is the part of the reef that faces the winds and the waves of the open ocean. They're kind of like the fortified outer part of the reef. So we have big, heavy bladed forms here that can withstand that wave action and can even withstand a lot of hurricane type activity. Taking a closer look, here we have the floor of this shallow platform marine environment. You'll see some things here like blades of seagrass. This is Thalassia testudinium, and the finer grass is called haliduli. Now these aren't names that are important for this lecture, but just to give you a feel for what's growing here, this is the type of seagrass that holds the sediment in place, just like grass in your lawn holds the sediment in place. Importantly, lots of little carbonate producers grow on these blades of grass. So where these blades look white, it is because there are foraminifera and other carbonate-producing organisms living on the surface of that grass. Here we have another image of the bottom. Water here is about 10, 12 feet deep, 3 to 4 meters in depth. And what you see are some lumps here. In some cases, they represent shrimp mounds, the burrows of the ghost shrimp. And in other cases, they're chunks of calcium carbonate. Like this is an old conch shell. Conch shell, conch shell, conch shell, so on. So there are conkers here. There are people that collect these and pull the snail out and pound them with a hammer and make soup out of them. This is a close-up of a patch reef. These are isolated, small, reefy structures that are located in the back reef portion of a carbonate platform. And you can see it looks like it's been eroded. There are some healthy living corals here and some dead, kind of chewed up looking corals here. and the base of the patch reef is also being undercut. So it's as if something was grinding away or chewing this up. This is using my head for scale. If you imagine a basketball, it's about the size of my head. So we can see that these corals are about basketball size. And we'll notice there are some robust brain corals here and some more delicate branching corals here. Now these are easier to break off, but they're also known as fire coral. So if you do bump into these, it feels like fire. Now you notice again a lot of debris beneath me here. This debris is going to be generated by the organisms that live in this environment. So everything you see, except for me, for the most part, is calcium carbonate. Some other critters of the deep. This is a stingray. This is what killed the crocodile hunter. He swam over one and the stinger popped up and got him right in the cardiovascular system. Now, the role these play in this lecture is, you'll notice you can't see the mouth of this fish. It's because it's underneath, on the bottom here. What these do is they cruise along the bottom and they take in shells, clams, snails, other carbonate producers, and they grind them up in their teeth, and they poop out the sand that is made of the ground up shells, the ground up snails and clams. So they're sand producers. A lot of the sand you see out here in this grass is generated by animals like this. Here we see just another image. This gives you an idea of here's the stinger, the stingray. A friend of mine stepped on one of these in Panama, and she passed out from the pain. So apparently it's pretty painful. This is a pufferfish. When these get agitated or excited, they suck in a bunch of water and they blow themselves up into spiny balls, spiny basketballs. Here we have an eagle ray and a stingray together. Now you notice the eagle ray has a mouth that's here in the front. So as in the case with many fish, the mouth tells you what they do for a living. The position of the mouth, in this case, tells you whether you're a bottom crunchy feeder or someone that's scooping prey out of the water column or just off the surface of the bottom. Again, you see some large shells here, conch shell, conch shell, conch shell. These are aragonite. In fact, everything you see here is aragonite. It's calcium carbonate, but it's not calcite. It's aragonite. This is a sea turtle. It was the subject of the photo at the time, but in reality, what I'm using this photo for is a pile of debris here of the old conch shells. Some were fairly recent. Some have been down here for 10 or 20 years. Eventually, these would all be cemented together into a coarse grained limestone. This is what it looks like in the beginning when they're still loose grains. Here we have a close-up of a brain coral that again looks eroded, and it's surrounded by bits and pieces of corals and algae. All this debris here. If you were to scoop this up, it would look like oatmeal flakes. Here we have a close-up of some other types of algae. Some algae here that's soft, no carbonate in it. And then there's this high magnesium calcite producing algae here. This is an Amphiroa. There's some goniolithon here. These are about 15 mole% magnesium. So calcite, but unstable calcite because of that magnesium. Here we have one of the main movers and shakers on the reef. This is a parrotfish. It's called a parrotfish not because of its language skills, but because of its beak. This beak is used to chew coral up. So the fish rips chunks of coral up, chews it into sand, poops out the sand, and extracts the organic matter as food. Each one of these fish can produce about 1 to 2 tons of sand per year. 1 to 2 tons of this carbonate material. Again, most of this is going to be aragonite originally. Here we have just some more close-ups of the reef. We see some branching corals here, fire coral. And we see schools of fish hiding from the barracuda here. And again, the fish are schooling in response to some predator threat, which is a barracuda that is just out of the image here. And you've all seen these probably. This is a moray eel. It's not threatening me. They breathe by opening and closing their mouth. So it looks like it's threatening you, but it's just breathing. And for our purposes in this lecture, you can see lots of carbonate grains here. And you can see a couple of the producers. This is Penicillus. We'll take a closer look at this in a minute. Another Penicillus here and here. These produce aragonite needles. This coral is aragonite as well. And this clam is mostly aragonite, but with a little bit of calcite. Now, if we take a look at the algae that does most of the work, we have Halimeda here, Penicillus here, Rhizocephalus here, Acetabularia, and Neogoniolithon. So some interesting facts about each of these. Acetabularia, these are known as mermaid's wineglass. They are about 3 centimeters to 5 centimeters in height, and they're a single cell. So this whole thing, 3 to 4 centimeters in size, is one single cell. So they're very important for biologists that want to study cellular activity without looking at a very, very tiny microscopic cell. Goniolithon, this is a high magnesium calcite producer. It looks like chow mein noodles when it's broken up. This is going to be an important carbonate producer in some reef environments. Halimeda here is an aragonite producer. Each of these utricles is about the size of an oatmeal flake, and therefore when this breaks up after death, it leaves a pile of oatmeal flakes behind. This is Penicillus, merman's shaving brush. It produces very, very tiny grains of aragonite that form carbonate mud, very fine mud. Rhizocephalus is another aragonite needle producer like Penicillus. So when this disarticulates after death, it just leaves a pile of very, very fine-grained carbonate mud, aragonite. So aragonite, 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 calcite. Okay, so we're going to take a trip to a faraway land, Ireland. And we're going to be looking at some images that were taken from around here. This area is called the Burren. And if you're to visit this part of Ireland, it looks a lot like the surface of the moon. It's a very neat, kind of special environment. In fact, there are some plants here that are only found here, nowhere else in the world. So I'm leading a group of students and professors in this case. So Hank Mullins from Syracuse, Adam Burnett from Colgate. We have Cole from Saskatchewan, Chris Holmden from the geology department here, Dario Kelly from Saskatchewan, Aaron from Pennsylvania. We're walking through this limestoney portion of Western Ireland to get to the other side of this carbonate-producing lake. We're going to take a core of this carbonate lake to reconstruct a climate record for the area. So this is the coring operation here. This is a push core. So we have a handle here that's connected to a core barrel and a rod. And you get a couple people that are 6 foot tall or so to reach up above their heads and push this thing down into the sediment. Keep track of where you are at all times. And then you extract the core. So you put your heavyweight people on the end and you push this barrel against this square rod and the mud comes out the other end. So I'm here to catch the mud. We've got this group pushing against this group here. And this is extrusion of the peat that's found near the surface. As you can see here, this is all organic matter. And the organic matter is made up of this stuff, this grass and mosses and other things that form peat. And here's the good stuff. This is pure calcium carbonate, pure calcite in this case. And this calcite, much like the calcite in those marine environments, is going to give us a good record of the ancient environment of Ireland, in this case going back about 16,000 years. and it's made by this. These are Terraphytes. They're freshwater carbonate producing algae called macroalgae because they're the size of about a half-meter tall plant. You've probably seen these growing in aquaria, or you've seen some plastic versions of these for sale in pet stores. Now, if you reach into one of these lakes, and we have them here in Saskatchewan, so you can do this when the ice melts, and pick up some of this stuff, it'll feel gritty. And the reason it feels gritty is because it's algae with tiny little rhombohedral grains of calcite growing on the surface. When this plant dies, all those little grains of calcite accumulate in the sediment pile. And this has been going on since the Jurassic. This is a limestone sample that shows a freshwater algae cross-section that is around 200 million years old. So these have been around doing this for a very long time. Common names for this plant include stonewort. So if you hear somebody say stonewort, they're talking about a charophyte. Again, these are calcite producers. We've been talking about all the aragonite producers in the marine world. In the freshwater world, it's mostly calcite producers. When we break these down into categories, major chemical and biological sedimentary environments, when we talk about shoreline and marine environments, as we have for the last few minutes, we have carbonates. They're produced in reefs on the platforms. So the corals that we saw earlier, platform would include the Bahamas, Florida Keys, Guantanamo Bay in Cuba. And deep sea, I don't have any pictures of the deep sea. Can't hold my breath that long. The precipitating agents are shelled organisms. It says some algae. This is the most important thing. Most important, algae. Inorganic precipitation from seawater. So this is when the seawater dries up. We get to the point where seawater is evaporating. Then we can have inorganic precipitation from seawater. The resultant sediment includes carbonate sands that were pooped out of fish and mud that comes from either the constant chewing by fish or from those very fine-grained Penicillus and Rhiphocephalus aragonite producers. And then, of course, the reefs are the most characteristic, big, bulky corals. In evaporate deposits, we can have evaporation of seawater, resulting in the mineral gypsum, calcium sulfate, halite, sodium chloride, and lots of other salts. In the deep sea, the shelled organisms go away, the calcite-producing organisms go away, and what we're left with is a fine residue of radiolarians and diatoms, the silica producers. In continental settings, we have evaporate deposits, like the Great Salt Lake. Some people can't even stand the word Salt Lake. This lake water is going to go away, leaving ions behind that include halite, borate minerals, nitrates, carbonates, and other salts. And lastly, in wetlands, we saw a hint of this in the photos from Ireland just now. We have vegetation producing much of the sediment. And this vegetation, once compressed and chemically worn down a bit, becomes known as peat.